Let's get started. And it's great to have everybody here. I think we continue to try to pull us all together. And one of the nice ways of doing that is really sharing a little bit about some of the exciting new things that are happening in and around the Beckman Institute. And so for today, I wanted to bring on Sam Tawfick, who is a part-time member in the Autonomous Materials Systems group and has really, I think, an exciting program that integrates materials and fabrication methods. And it probably has roots in, his early childhood, I guess, when exposed to engineering concepts from a very early age. Sam went on from there to earn his PhD at Michigan and postdoc at MIT before coming to the Mechanical Engineering and Science Department here at the University of Illinois, where he's now an associate professor and, as I said, part-time member of the Beckman Institute. Sam runs the Kinetics Materials Research Group, and as I said, really all about using and understanding materials and how they can be made in form and function and that form and function achieved in some unusual and unique ways, and also deliver function that is quite unique and interesting. And so today he's going to tell us about morphing hair, artificial muscles, and the future of automation. Sam, thanks so much for presenting the director's seminar.
Thank you so much, Jeff. It is truly a great honor to be able to present my work in the Beckman Director Seminar Series. It's one of my favorite seminar series personally. I actually did a lot of work on these slides because I really value this seminar series, so I try to organize them a little bit more. So I'll just get started. Can you all hear me okay?
Yes, perfectly.
All right. Let me move this to the side. So I like to start with this video.
While preparing for a lecture, Orsted noticed that when he connected a copper wire to a battery and held it near a compass, the needle moves. That may not seem much now, but that's the beginning of electromagnetism. The first demonstration that electricity and magnetism can create motion. Faraday used these two critical discoveries to tap into the universe's very own power system. Here in his workshop at the Royal Institution, Faraday showed that electricity, magnetism, and motion are all firmly linked. Just a year after Orsted's discovery, Faraday designed this. There's a wire that goes into a pool of mercury to which a magnet is attached. And when you pass a current through that wire, watch what happens. Believe it or not, this is the world's first electric motor.
So I really liked to start with this experiment. I actually love this science experiment. And the reason I love it so much is I feel it represents so much what we are trying to do, especially at the Beckman Institute. We can simply say that this science experiment in 200 years later today has significant impact on our society. It has a huge impact on the manufacturing industry. It is the working horse of the manufacturing industry. It drives scaling and innovation. It also is more recently enabling ideas like democratization of manufacturing through 3D printing. And it's enabling a whole new age of robotics, bio-inspired robotics that can serve human and in the most extreme environments. So looking at all of these innovations, one wonders, are there any limitation to the electric motor? It seems like it has driven our society in a way that couldn't have no one could have imagined before. So the answer is yes. There are a ton of limitations to electric motors. And I like this example because it shows many of the limitations of the current electric motors in actuation. What we're looking at here is facial expressions, of course. And facial expressions are examples of very dense degrees of freedom actuation, coupled with truly elastic and complex motion geometry. This doesn't only enable actuation and morphing, but you can think about also small-scale manufacturing. Think about forming materials into final shapes using such dense forms of actuation. The other limitation is, of course, not only the density of actuation, but the size scale of actuation. Small scale actuation is impressive when you look at insects. The number of muscles and the organization of muscles and the mechanical design on such a small scale clearly shows that we are still a very long way from, for example, small scale robotics. These two examples exemplify the limitations of electric motors. So in my talk, I will show you some of the exciting work in our group in two directions. One, in using morphing hair actuated by capillary forces. This gives you very dense degrees of freedom actuation, and it enables small manufacturing and complex shape change at small scales. And the other example is using fibers as artificial muscles that can mimic human muscles by contracting when stimulated. In this case, these muscles are stimulated electrically, they heat up and contract. And I'll show you how these open up opportunities in small scale actuation for robotics. So I will start by the artificial muscles, and the first example is what we call coiled artificial muscles. For those of you who are not familiar with these muscles, I'm starting with the simplest example. The example of a nylon artificial muscle that is coiled in a very specific way, and it's heated with an electric wire. And you can see in the middle video, you have the IR camera, you see the heating distribution, and it can actuate by lifting a weight against gravity. So of course, you can tell how good this muscle is by looking at how much weight it can lift. This will be the muscle stress, and how much stroke is the actuation. So the distance of moving the weight up is called stroke. So why do we work in my lab on these twisted muscles? Simply because they are superior in terms of balancing this strain to stress, or a stroke to stress. So on the x-axis, you see the stress. On the y-axis, you see the strain. And if you look at any type of actuation technology, you see that the slope is this negative slope that represents the trade-off between strain and stress. Of course, if I take any one type of actuator, I add a higher resisting force to its motion, then the actuation strain is going to decrease. And this is interestingly universal, regardless of the actuation mechanism. So we have like pneumatic actuation, which is very different than dielectric elastomers or piezoelectric material, magnetostrictive, shape memory alloys. All of them suffer from the same trade-off. But for some interesting reason, twisted muscles are superior to all of these. Actually, although we've spent a lot of time on the theory of artificial muscles, we still cannot say in very simple words why they perform so well. It's a combination of so many things. But definitely one of the most critical things is their interesting geometry. These twisted and coiled artificial muscles are not simple helical spring. If you get a helical spring and you heat it up, it will not work like a muscle. They are twisted. They're actually so highly twisted that the elastic energy stored in these muscles is already very high at any state. When you heat up this muscle or cause them to swell chemically or electrochemically, the shape of the coil, as you can see on the top right image, changes by the untwisting of the fiber caused by the swelling. When you have highly twisted, for example, molecules or fibers on the external diameter of this fiber, these highly twisted fibers, their orientation is very sensitive to how close they are to the center of the fiber. So when you swell this material and push these highly twisted fibers away from the center, this causes dramatic untwisting and hence this large actuation. So twisted muscles actuators use geometry to enhance their performance and stored elastic energy. So this is a video of how we make these muscles in our lab. This video is made such that you can clearly see the twist and not only the coiling action. I can play this video again. So there is a motor connected on the top of this fiber, and we drew a line with a Sharpie literally on the side of the fiber. And the black lines that you can see are resulting from the many, many twists before this coiling instability takes place. So the first lesson we learned is to make really unusual actuators, you have to come up with unusual fabrication techniques. In this case, we're using elastic instability as a part of the fabrication technique of these artificial muscles. The second thing we learned is that because these muscles are so unusual in their geometry compared to electric motors, we shouldn't expect to use them as like simple rigid parts connected to other rigid parts, like in most actuation currently in automatic systems. Instead, there are many opportunities in using these in unusual geometries like braids and textiles and so on and so forth. So the roadmap for artificial muscles to one day drive automation includes improving each one of these features: scalability, strength, life, rate, stimulation, efficiency, stroke function. I can speak about each one of these, but I'll focus in this talk on just a few of them. These are the few that we believe are most critical and that we've done some work. So we've done some work on strength, stimulation mechanism, stroke engineering, and function, how to use this interesting geometry and make a functional design. So the work that we've done on strength was actually the simplest work, but it was very well received. Original artificial muscles were done in using two material systems. One of them is using carbon nanotubes with a wax. Carbon nanotubes are short fibers. You can make a yarn made from carbon nanotubes, but these yarns unfortunately are not so strong. And the reason they're not strong is when you have short fibers, you can't achieve the same type of strength you have when you have continuous fibers. So the other type of artificial muscle is one made from nylon. And of course, it doesn't have the strength of carbon nanotubes or the strength of carbon fibers. So what we said is, it seems very simple to make an artificial muscle. You simply need to find a continuous fiber. In this case, we went to the strongest commercially available fiber, which is carbon fiber. And you use a matrix that can swell or expand due to different types of stimulation. We used the simplest matrix possible, which is PDMS. We didn't do any functionalization between the fiber and the matrix. And we found that if you twist the bundle or the toe of fibers with the PDMS inside it, and there is some interesting curing steps involved and so on and so forth, then you can make artificial muscles that actually perform really well. And the reason they perform so well is they're so strong mechanically. So they can indeed lift large weights without breaking. We stimulate them by swelling them, for example, in this case, using IPA or acetone in the middle video, or by passing a current in the carbon fibers. They electrically heat up and you get a contractile motion. We demonstrated that we can use a very simple equation that describes the actuation. To our knowledge, this is the first equation that can describe the actuation of a coiled artificial muscle in its coiled geometry. We used an existing old equation derived many years ago that describes the elastic instability that causes a straight fiber to become a coil when highly twisted. And what we found out is the actuation that you get is simply two different equilibrium configurations of this coil. If you have the same applied load T, you get different configurations with different angle beta. So beta can be described as a function of the material properties of the fiber, bending stiffness B, shear stiffness C, the applied load T, and of course, the stored elastic energy that caused this bending, which comes from R. So R is the twists per length. And using this simple equation, we got very good agreement between experiments and simulations, even at a varying number of inserted twists. So the second example I'm going to give you on our work on artificial muscles is different types of stimulation. And in this case, I'm using carbon nanotubes in the form of yarns. So my collaborator at the University of Texas, Ray Beckman, he's the inventor of coiled artificial muscles. He developed these muscles initially using paraffin wax as a simple material that expands to heat. More recently, he started working on electrochemical muscles, and this new type of electrochemical muscle is called unipolar electroosmotic pump muscle. So instead of the pure carbon nanotubes, we coated carbon nanotubes with an ion exchange polyelectrolyte, such as PSS or Nafion. And this polyelectrolyte shifts a little bit the potential of zero charge of this muscle. And due to this shift, when you put it in when you apply a voltage, due to the electrochemistry, you get the ions to go in and cause swelling. But by shifting the potential of zero charge, two very critical things changed about this muscle. The first thing is one of the limitations of electrochemical muscles is that you can operate them only within the electrochemical window that is stable, beyond which you start getting other side effects. So from -1 to 1 volts, for example, is the electrochemical window. The potential of zero charge is initially for the pure carbon nanotube muscles close to zero. So in both cases, these muscles swell. So if you apply a positive voltage, they swell and actuate. A negative voltage, they swell and actuate. So you can't utilize the full electrochemical window in this case. So these are what we call bipolar muscles. The unipolar muscles, on the other hand, you can shift the potential of zero charge outside the electrochemical window. And by doing this, you can be adding, by going from a positive voltage to another voltage, you keep adding ions. And when you do that, you get a larger stroke. So we got a little bit of a higher performance due to that. The other interesting feature is that because these are ion exchange membranes, what happens is the size of the ions that swell the artificial muscle is a function of the applied voltage, such that when you apply the rate of application of voltage, such that if you apply the voltage at a faster rate, the effective size of the ion, the hydrated ion that goes inside the muscle and causes it to swell, becomes larger. And by doing that, we were able to overcome one of the biggest limitations of electrochemical muscles, which is that they're very slow. So as you can see here, by comparing bipolar to unipolar muscles as a function of frequency, in all cases, as you increase the frequency, the muscle performance, for example, the stroke drops a little bit. But with the unipolar muscle, you start with a much higher value, and you kind of maintain it up to a large frequency. And the reason it doesn't drop completely is because of this larger hydrated ion that you can get into the material when you apply your voltage. This was verified by doing some calculations to measure the stroke charge ratio. So how much stroke is obtained per unit charge getting inside the material as a function of the scan rate. The black line is the old type of CNT muscle. This is the neat CNT muscle. And then you can see these red and green and the other square markers. These are with the ion exchange membranes. You can see that as the scan rate is increased, the stroke to charge ratio is increased. Combining this with other innovations to increase the strength of the material, in this case, we added graphene oxide to the carbon nanotube yarn in a special concentration to enhance the strength. We are eventually able to make muscles that have an incredible performance. Some of these muscles reach 10 watt per gram power density. This is basically comparable to the power density of the motor inside the Tesla cars. So such a high power density coming from such a simple fiber that, that actuates just by swelling due to an applied voltage, we think that this is very promising. The other reason it's promising is, of course, the electrochemical muscles can be potentially more efficient than thermal muscles that dissipate a lot of thermal energy. So the third part I wanted to discuss with respect to these coiled artificial muscle is going to bridge me to how we make functional machines using these muscles. So as I talked about previously, there is a trade-off between applied stress and stroke, and similar trade-off between applied stress and energy density. But what I didn't discuss is at very, very small stresses, there is another bigger limitation with coiled artificial muscle that's not present with any other actuator. If you use a coiled artificial muscle without applying any stress, so at very low stresses, the coils will be touching each other. And if the coils are touching each other, you can't get any stroke, you can't get any contraction, even when you stimulate this muscle. So a good muscle would be a muscle with so much stored elastic energy, just like this muscle, but where the coils are not touching each other. This is what we're calling the separated coils, even at very small applied stresses. So we had to basically do that because any functional design that you need to make, for example, a robot, cannot operate if the muscle is under very high tension all the time. In many designs, what you have is a mechanism that is some sort of a spring-loaded mechanism. We represented like this image, where the spring is initially not stretched. And then when the muscle contracts, the spring, which is your machine, starts getting stretched and starts moving. So you can do that, which is like the simplest machine possible. You can do that with the current muscles because they need to be preloaded to start operating at this point. So they need this initial applied stress to start giving you a useful tensile stroke. So we developed a method, and recently, a lot of this is not published yet, on making these muscles that where the coils are not initially touching. And the way we did that is, instead of the original video where we kept twisting until we get to this buckling instability that forms the helical coils, here we stopped the twisting right before the onset of this coiling that takes place. And we connect another fiber. This new fiber that you see here is chosen diameter to enable a lot of the details of the geometry that we get. But the goal of having this this other fibers that you will see is this becomes the internal core of the coils. And when you do that and you adjust, for how much stored potential energy is, and then you do your annealing, in the right way possible, you can eventually dissolve this inner core fiber. So it's a water-soluble fiber core. And once you dissolve that core, you form an open muscle like the one I showed earlier. And this enables all of the kinds of functionalities that we were going after. So this takes me to how to use the muscle in functional designs. So I'm showing here two examples of some of the functions we were very motivated to replicate, which is the jumping of small insects. On the left-hand side, you see the jumping of click beetle. This is work done by my colleague, Amy Wisa. And on the right-hand side, you see the trap-jaw ant, which was done by the Patek lab, as well as the Suarez lab here at the University of Illinois. In both cases, these jumps are actuated by a muscle, but in addition to the muscle actuation, there is always a complex mechanical mechanism that stores and releases energy to allow for these jumps to take place. So I'm going to start showing you some robots designs motivated by this goal of jumping. On the left-hand side, you can see schematics of how the click beetle jumps. So the click beetle has a muscle. The muscle is not shown here, but what is important is when the muscle stores potential energy into this configuration, there is a latch. And then it's able to basically trigger this mechanism, which causes an impact with the ground and then followed by jumping. So we decided to put these components in the simple possible mechanism that we can fabricate at a small scale. So this is a very simple schematic of how our machine works. We have an artificial muscle that is connected to two moving stages, a buckling beam, and basically a mechanical constraint, that middle section here. When the muscle actuates, the buckling beam starts going towards this mechanical constraints. And this is, of course, known as buckling, but buckling alone doesn't give you jumping. What buckling gives you is it gives you something that is willing to go from one buckling configuration to another buckling configuration through a mechanism called snap-through. The geometry is such that when you keep compressing this muscle, eventually the stored potential energy in this configuration becomes too high. And the system knows that there exists another buckled configuration with much lower energy because it doesn't have this constraint. So a snap-through event takes place. So we call this a self-triggering because it triggers itself with only one actuator. The same actuator that stores the energy causes the triggering. And then you get the impact with the ground and you get the jump. So this was the initial idea. So here is the implementation of this idea. You can see here like the robot, you can see the constraint, this rail. You can see 3 buckled beams and the artificial muscle. I'm going to show you a video of this first jump with an artificial muscle. This first jump was obtained a little bit over a year ago, right before the lockdown, the lockdown when the pandemic first hit the US. And we were very excited with this jump. Although it's such a tiny jump, it's the first demonstration that these artificial muscles can be coupled to like buckling mechanisms, self-trigger to get jumping. I'm going to take you through our journey to enhance this performance, and I'll show you where we currently are. So when we started working on, this simple system that has, an artificial muscle, a buckling beam, a mechanical constraint, some mechanical moving parts, we started realizing the level of details from the mechanical design perspective in all of these parts that can enable this jumping to be, much more effective. And we got really inspired by looking at, insects and insects evolution, and insects evolution causing small changes in mechanical design. I look at this image and I see all the different bends and details and small features on each one of these insects. And I have a lot more appreciation now on how each one of these is functional and took a lot of, effort from the evolution machinery to get to where it is right now. And I'm going to show you how we sort of did that for our muscle, for our jumping robot. So the jumping robot can be actuated whether on the left-hand side in general using pre-stored energy in a buckling beam like the one I just showed you earlier, or without any pre-stored energy. In each case, you can get sort of asymmetric snap-through type behavior, which is what I showed you earlier, or symmetric type behavior. And in whether symmetric or asymmetric, whether the robot body is itself bending or twisting, or it's fixed and sliding, all of the small mechanical details make a big difference. Eventually, our goal is to get the best jump, and not only the best jump, but to do multiple jumps. So you'll get to see, one of our favorite robots. It's not the best robot. I'll show you some different variations. I won't get into the details, but you can clearly see that this design is becoming much more complex than what we started with earlier. You can see interesting details like this protrusion here that interacts with a very special way with this rotator that is shown in pink to cause the buckling snap through to happens in a very to take place in a very specific way. Lots of details that I'm not expecting you to follow, but I just wanted to tell you the value of mechanical design when you're trying to combine artificial muscles with buckling beams. So this is a high-speed camera on the left-hand side of the jumping. You can already see how this jumping height is much more exciting than what we had earlier when we started before this evolutionary design. You can see on the right-hand side, orders of magnitude higher jumping achieved by small variations. And this is just a video that I really like because it kind of shows a little bit our approach to designing the snap-through buckling. So on the right-hand side, you see a force displacement that for some reason, I'm not sure why it didn't synchronize with the video. I'll play the video again. So this is a video of putting the robot on an Instron machine in compression, watching from the side how the initial buckling takes place, interacts with the robots with all these little details, how the force displacement profile is, and what type of muscle is needed to accommodate this force displacement profile until you get the snap through. So the snap through is the event where the beam moves from left to right, and this is the event that causes the impact with the ground and the jumping. So this is one of our most recent robots. This one is capable of consecutive jumping. It still cannot self-right itself. So if it falls on the side, the student has to come in and hold it and put it in the correct orientation. But as you're watching in this video, you'll see that after some time, this the snap through goes back. It's designed to go back to its initial configuration. And this is when the student is going to come in and touch the robot and put it back in its original configuration. And then we repeat the actuation one more time to demonstrate that this mechanism is capable of multiple jumps. Okay. So how good are our robots? So I showed you, different types of robot designs. These are the short names for like asymmetric versus symmetric. P is pre-stored energy. Not having P is no pre-stored energy. And one way to think about the effectiveness of these robots is to put on one axis the size of the robot. On the other axis is the jumping height to size ratio. So on the right-hand side of this plot, you can see all of the big robots. Of course, big robots can be very effective in jumping because they can use the best electric motors, the best materials for springs, and the best mechanisms and ball bearings and everything, that is most advanced and then can be done at this large scale. On the left-hand side, you can see all of the insects that we were able to find in the literature. And our robots, our current robots, are these 4 red points. So you can see that, if you look at the trend of this in general, there's clearly like a slope, governing the trade-off between the size and the jumping effectiveness. And we're kind of, pushing the limit of this trend. It makes you appreciate also fabrication technology and its limitation. If we can push these red dots a little bit to the left by decreasing the size on this log scale by just like 1/2, we will be clearly demonstrating that our robots are definitely more effective than anything that can be done in the natural world or in the large sized robots. And this is just a developing image of our army of jumping robots. I don't like the word army, but I don't know, it just came to my mind now. So I finished the right-hand side of the talk, which is the artificial muscles. I told you many stories about how we make the muscles better, how we make them suitable for actuation, and how we make functional designs. I'll switch to the left-hand side, which is the morphing hair. And the ability to do actuation on a small scale in a very dense fashion. Again, I'll start with an example of carbon nanotubes. This is my PhD work. I won't be talking a lot about my PhD work, but it's the motivation to the new work I'm going to show here. So in my PhD, I used self-organization of carbon nanotubes to create these interesting geometries on a very small scale from carbon nanotubes that cannot be fabricated using any other technique. So this was, the goal is manufacturing, texturing at the nanoscale. The process or the mechanism of this shape change is elastocapillarity. Elastocapillarity is basically the simple idea of when you have 2 hairs and a meniscus of liquid between them, due to Laplace pressure, you have a negative pressure in the liquid that drives the self-assembly of this hair. That's a very simple schematic compared to, for example, what you see on the top right corner, where you see literally hundreds of thousands of carbon nanotubes with very interesting geometries and also some instabilities taking place that lead them to this, for example, helical configuration. On a simpler geometry, what you have is a perfectly round carbon nanotube pillar that is very low density carbon nanotubes. You wet this pillar, and what you get is this dense bundle with tree-like buckling and roots that organize themselves due to the balance between elastic forces and capillarity forces. So the issue with trying to study this on carbon nanotubes is it's a very small scale, and carbon nanotubes are very dark. It's also a very fast time scale. Basically, in situ experiments that should allow you to observe this mechanism is almost not possible. So our approach was to really try to scale up a carbon nanotube bundles as big as we can, as long as the surface energy of the liquid can allow us to do that. And the biggest system we were able to make is a system that consists of carbon fibers instead of carbon nanotubes, which means we scaled everything up by 1,000 times, maintaining the right scaling and the distance between the carbon fibers and so on. And we started studying a very simple but interesting system where we put the carbon fiber, organize them into a hollow bundle. And we observed that when you submerge this hollow bundle and then drain the liquid from the hollow bundle, you can either self-assemble them into a closed bundle or an open bundle, depending on how fast you drain the liquid. We set up a system in the lab to be able to observe this, and you will see a video that kind of shows this process. So you're looking on the left-hand side on the top view, the right-hand side, the side view. This is what we call slow drainage. So the original bundle, you know, as it's drained slowly, it self-assembles into this open bundle. But when you drain it fast, you self-assemble into this closed bundle configuration. And it's fully reversible. You can do it many times between open, closed, open. The interface between the carbon fibers can be lubricated by the liquid every time. So of course you can imagine, you know, once we did this experiment, we found out, well, now we can observe it. It looks cool. We can get lots of information from these videos, and let's try to understand the information from the videos. So what we did is we started looking at the time scale or the evolution of the shape as a function of the drain distance or drain speed. So looking at the bottom here, you see the drain distance. So we're moving the liquid down by h, and we can observe the radius evolution. You see the two black markers. This is the external radius and the internal radius. And then the orange marker is the mean radius. And you can clearly see that in the case of aggregation, which is the slow drain rate, there are two stages. There is this initial stage where basically the wall of the bundle thins down. So the black markers get close to each other. And then once they thin down, they start, the radius starts decreasing in the second stage. So we call this the shrinkage stage. So thinning and then shrinkage. On the other hand, for the case where you get the full closure, we call it also sometimes the flopping behavior. There is no thinning stage almost. You just get, you know, all of the fibers moving at the same time towards the center, and you get this closure right in the beginning as you start drainage. So we started developing scaling laws to describe this behavior. I won't go through a lot of details, but you can imagine that, you know, to develop these scaling laws, you have to fabricate many, many bundles with different inner and outer radii, different length. And then for each case, you track the evolution of radius, mean radius versus drainage distance. And if you can somehow collapse all of this data on a single line, then you found the right scaling law, which is what is shown in C. So the way we did that is kind of just taking advantage of the first thing is what we call elastocapillarity length, which is the ratio between bending stiffness and surface energy of a liquid. Then we defined a non-dimensional radius, that's the radius during closure, which is a function of the displacement, that's the inner displacement as a function of drain height, so we call it delta H. We used a non-dimensional drainage height that comes from the drainage distance, the length of the fiber divided by LEC, and we defined an aspect ratio. The way you can derive this law needs you to have a relation between force and displacement. So that's delta H. Delta H is what connects force and stiffness of these fibers as they're moving inwards. That force and stiffness is what took us about a year. That scaling law that goes inside delta H to describe the force stiffness relation is very complex, because you have thousands of fibers that are constantly rearranging themselves. They're not simply moving as a rigid body. So you have rearrangement and you have jamming. And if you can write down a scaling law of the stiffness evolution during rearrangement and jamming, all of this becomes easy. So we were able to write this law, but it's not an elegant short formula. You can read it in our papers. Reviewers actually, kept pushing us, can you simplify it further? And we said, we can't. It's just, we're still trying to simplify it, but it's complex motion. You have thousands of fibers that are jamming and rearranging as you're shrinking the size. We did the same thing for the dynamics. In this case, you can see we have the velocity of drainage versus the aspect ratio. The filled markers are markers that closed, and then you have the open markers, and you can see that, when we apply our scaling laws, we can get clear division between the open and closed markers, and we can get a scaling law that shows where this division is. We were able to do that by finding the right time scales. I described earlier that there are two stages, an aggregation stage. This is governed by a time scale that balances the capillarity-driven pulling of two fibers close to each other and the viscous dissipation as the liquid tries to escape between those two fibers, and the closure or flopping time scale, which is governed at what happens on the macro scale of the bundle. When the liquid trapped inside the bundle, this liquid in this controlled volume, try to escape from inside to the outside due to the pressure gradient through the fibers, but the fibers at the same time are thinning and they have a time varying permeability. Balancing these two scaling laws enables us to find this trend. So, we were very excited that, we found out like how manufacturing for carbon nanotube assemblies work by scaling up the system to carbon fibers. The editors of physics, where we submitted this article, found that as just a cool way of hairstyling. So I found that title a little bit funny. I like it. So there are many other types of interesting, completely unexplored morphing phenomena that can happen to bundles of hairs when they interact with liquid at different time scales, so at different drainage speeds. Some of them are shown here, which is triangular bundles, square bundles, and pentagon bundles. You can see the bundle final shape is a function of the drain speed. You can see interesting morphing that happens, like, for example, this circle formation of the original triangular bundle, or the square bundle also making that circle, and the pentagon also making that circle once the speed is high enough. So we currently have a model that describes this, and we're preparing a paper on it, but I will not spend a lot of time talking about it. I just want to wrap up. So before I wrap up, I have 3 more slides. The first slide is, this one that shows you that we have a library of morphing transformations that allow very dense actuation just by combining elasticity and capillarity. I showed you examples from the ring type shapes. I will show you a couple of examples from fins. The key thing about fins is the 2 configurations that you have is vertical configurations where fin can come together and pierce the surface, or horizontal configurations where the fins completely collapse. We found that to be very useful for engineering applications. So we make integrated systems now. We're not using a reservoir or a linear stage anymore. What we have is microfluidic channels that control the flow of liquid in and out of the surface, and the surface has these fins that deform. So examples of the devices that we're making. are devices that have fins that can move to the left or the right based on how the fluid flow is directed. We have these double fins that can also move to the left or the right, or can coalesce and pierce the liquid surface and remain vertical. As you will see, controlling all of these configurations is through controlling the rate of liquid drainage. We have interesting blooming flowers that can completely open or close based on different rates of actuation and geometry. We can make overlapping fins that can go in one direction or the other direction. And you can start thinking about the application of this in like reflective displays and other types of morphing surfaces. And of course, just like the first thing that comes to your mind if you're at the University of Illinois is show how much you like your institution by demonstrating that you can write its name using whatever you're doing. In our case, it's morphing elastocapillarity systems. You can show that we make these pixel arrays that can write UIUC. So this is the end of my talk, and I have a very short summary. So the summary is there are many opportunities to bring these bio-inspired materials and processes to new types of robots and innovation. These take advantage typically of complex mechanics. Response is unusual and typically nonlinear. By definition, because of all the innovation and the geometry and elasticity. Designing real engineering systems require new methods for evolution-inspired co-designs. You can't just think about it like we used to do in the past or in my earlier training, where you get an electric motor, you design a rigid machine of linkages and you put them together. Everything is deformable and co-design methods are needed. And the last point I wanted to make is a technology roadmap could enable adoption of these new actuation modalities. I would like, of course, to acknowledge my team who does all of this work, my postdocs, graduate students, and undergraduate students who contributed to all of this work, and the funding from the agencies and the industrial partners that believe in this work on new types and modalities of actuation. So with that, I would like to thank you for your attention, and I can take questions.
Thanks so much, Sam. That was really well done. You did do a great job taking and preparing the talk for the very wide and general audience that you just delivered it to. So I appreciate you doing that. It's fine to unmute your mic and ask a question for Sam if you have them now, or you can put them in the chat and we can read them from there, whatever's easiest. I'll get started, and my question really is, thinking about the limitations. Would you say that the biggest limitation to achieving a desired design is in the materials, in the fabrication process, the mechanisms of actuation? Where if you had to point to one thing, what would you say, I wish we could have better, and what would that be?
I would say the combination of fabrication and materials. So fabricating with the right materials. So for example, I can drive fabrication down using, let's say, MEMS techniques, but these are typically not the right materials. Most MEMS type materials don't have fracture toughness, which is what you need for a functional device. If you can do if you can use fiber reinforced materials and microfabrication, then of course that would be very useful, but you can't do that. So I think it's there's still definitely a lot of room for like getting, fabrication on smaller scales with better existing materials.
Great. Thank you. Randy, go ahead.
Hey, thanks, Sam, for the great talk, and Jeff for hosting such a great series here. Sam, thinking about limitations also, I'm thinking about the first part of your talk. And I don't know if you can easily go back to slide 29, somewhere near the end of the jumping robots, you had this nice plot of, the jumping height as a function of the size of the robot.
Yep.
And in seeing that, this one on the right, you do such great scaling analysis. For example, with the elastocapillarity, I see a plot like this, and it just seems to beg for a scaling analysis for what the limitations might be. In theory, even if you made a robot that was 10 times smaller, are there power density limitations? What's the limitations of like a box you can draw around this of what we can currently do with known power systems, for example?
Yeah, that's an excellent question. So in this case, the limitation will be, I think it's material properties, and it will be like the theoretical limitation. And it will be something like the fracture strength squared divided by the modulus. It's something like that. There is a scaling law that looks like this, which is the scaling law of what is the highest potential energy you can store in a material. So that is definitely function of these two. The strength of the material, because you want to store more elastic energy, and at the same time maintaining that high modulus that allows you to store a lot of elastic energy. So that's scaling.
Yeah, and that assumes it's the same mechanism, right? Given that mechanism, what's kind of the limit there? But I also wonder if you've thought about other mechanisms. Like there's no way a AA battery could ever make an object this size jump that high unless you're storing that energy in a capacitor or something else that can release it as a power density rather than energy density. And I think those would, have lines that are way lower than all of these insect jumps, for example.
Absolutely. So I was referring to the mechanical design aspect. You're right. There's also the power source aspect. Of course, will have a limitation as well.
It's cool. I think your approach here will beat all of those other limits, which is why it'd be really cool to see that, because you're going to be way above it because of that particular, especially the power density aspect of how rapidly you can really release these things. Yep. Yeah, thanks.
Thanks, Randy.
Mariana?
I have a question. Yeah. Hey, Sam, fantastic talk. So beautiful. Can you hear me?
Yes. Yeah, thanks.
Okay.
Yeah.
I was curious if you've looked at maybe some macro scale systems like kangaroos and the fact that they can jump incredibly high, and the way that their tendons store energy is very similar to the idea of the coiled collagen embedded within those tissues. And the other thing that came to my mind was the high jump technique that's used for humans, and whether or not the constraint of keeping the mass fixed and not being able to change the center of mass location when you're trying to jump, would that be a design variable that you could incorporate to optimize the height? Because that's what happens when you do a high jump, where you have the pole vaulting high jumps. So here you have kind of a similar snap through mechanism that's used to get the pole vaulter over it.
Yeah.
So I was just curious your thoughts on looking at some of a different scale of bioinspiration, perhaps.
Yeah. So these are excellent questions, and we thought about these things a lot actually. There are basically two distinct types of jumping, and the two examples that you showed are from the same type of jumping. That's my perspective. That is different than what we do, and the difference is we rely on impact with the ground. The kangaroo jumping, I mean, I've never seen one in real life, but I don't think it relies so much. I know you did, I didn't. It doesn't rely, I think, so much on impact with the ground. It really uses its muscle combined with tendons that can store elastic energy, right, to jump. Or does it really impact the ground so much to jump?
I don't know. The tail of kangaroos is also a very important component, and the tail essentially becomes like a springboard lever to
Okay.
help assist with this.
Yeah.
But certainly the high jumpers, though, the only way they can jump is when the pole hits the target. And so then it would be, I would say, maybe more impact driven.
But yeah, it's still not impact. It's still, so yeah, it's stored elastic energy when the pole bends, but it's not instantaneous momentum transfer.
Right. I get you.
So our jumping is based on this instantaneous momentum transfer. Now, is there one of them better than the other in general? I cannot say that for sure, but for the practical limitations of our system, the one that we chose is better. And that's because we have this very lightweight beams that can quickly snap the ground and cause the jumping. That would be a little bit more difficult for us otherwise. It also, I think, I mean, even that I can say for sure, Mariana. Is there a way we can design something similar to the pole jumping? So no impact with the ground, but just storing potential energy and jumping and achieving a higher performance than what we do? Maybe yes. But, you know, it will take us time to really know definite answers to these questions because no one thought about them in the way we do, which is like, you know, designing systems and muscles and beams and, you know, getting it to jump and not only looking at the biomechanics.
Thank you.
Thanks.
Are there any other questions for Sam? Well, I don't hear any. Sam, that was a beautiful talk. Thanks so much for sharing that with the Beckman community. And we really appreciate hearing from you and others. And it's been a really great semester. This is actually the last of our director's talk this semester, but we'll pick it up again in the fall. So let's everybody give Sam a nice virtual round of applause, and we will see you soon.
Thank you so much.
Thanks so much, Sam.